time response, we have already started discussing.
They took these guys top five. Jesus was top five, top 10. He wasn't five.
And then, I would talk to some young kids, from Atlanta, neighborhood groups.
That's because they young, bro.
That's what I said.
Which you guys do?
The new one.
Alright, pay attention guys here. So, we're going to start discussing time response of first and second order systems. Now, before we get into this, let me introduce you to the concept of poles and sequence. Now, consider consider this system. Example. It is a very simple system. We have our pairs. Right? What does this mean? How do you write it? this as
C is equals n plus 2 divided by s plus
equals
5.
s plus 2 divided by, this is the transfer function. You understand? This is the Laplace transform of the output. This is the Laplace transform of the input. Okay. Now think about, if I say
Your pole is negative 5,
yeah,
your 0 is negative 2.
whole of the system is at s equal to negative 5 and 0 of the system is at s equal to negative 2. Okay. It's pretty straightforward, right? Is it difficult? So you can say poles are roots of the denominator of the transfer function. Does that make sense? Okay? And zeros are
Roots in the numerator.
roots of the numerator. Yes.
Is the reason they call poles because once you zero out the bottom, it goes to the plate.
Right, like that's exactly what it is. Okay. So here, if you look at 0, what is the characteristic of a 0? In this context, okay, not 0, 0, but what is the characteristic of this?
It makes the transfer function equal 0.
Yes, exactly. So if you substitute s equal to this value, it makes the transfer function equal to 0. Okay. And what is the characteristic of a pole?
Zeros are undefined, so it's like up and down.
Again, I'm going to tell you last time. This is undefined.
Okay.
This is undefined. This is undefined. This is undefined. Any number over 0, any number over infinity is not undefined. Understand, this is not undefined. Does that make sense?
So what is it?
Huh?
What is undefined?
Each circle is one is undefined.
This side is undefined. This side is not undefined. Now look at what is undefined and what is not undefined. What is this value? This value.
Zero.
Infinity.
Infinity. Why is this 0? Something over 0 is 0.
Oh.
No, that's
Infinity. What is this value?
Zero.
0. Okay. What do you get? What do you get a finite when a finite number is divided by infinity? What do you get? It's 0, right? It is. So this is 0 over a is
Zero.
0. Okay. Infinity over a is infinity. Does that make sense, Jessica? This is undefined. Okay, this is defined. This is simply equal to infinity. This is equal to 0. This is equal to 0. This is equal to infinity.
So like 2 divided by 0 is infinity?
Yeah. 2 divided by 0 is infinity. How do you divide 2 by 0? What is infinity? Infinity is a really huge number, right? It will approximately be equal to 0.
So like doing
Conceptually, you should understand this. If you have 2, okay, think about how you divide by, let's say, 2 lakhs. What are you going to get? 0.00000. Are you going to get that? So now make this infinity. What are you going to get? 0. No? If you cannot understand, just remember this. Okay? I don't want you to say something over infinity is undefined. Alright, now tell me what is this? What does pole do?
makes it infinite.
Makes it infinity. Okay. So pole will take the system to infinity. Can I erase this?
No.
Now, tell me what is the, in terms of stability, or let's look at it in the context of what is the time response of this, or what is the step response of, let's say, let's call this A. What is step response of A? We just did this in exam. CS is equal to S plus 2 divided by S plus 5 times 1 over S. Does that make sense? This can be written as S plus 2 divided by S into S plus 5. Alright? Now if you, what is C of T? Can I write C of T as, or if I take the partial fraction expansion, this C of S becomes A over S plus B over S plus 5. Okay, and C of T would be simply A plus B e to the power of minus 5t. You see that? So this is the time response. Can you draw conclusions with regards to the stability of the system, or
A support response and B even negative 5 using that.
stability? Yes. So that is, this is the forced response. This is because of the input. This is the natural response or the free response. This is because of the system itself. Can you draw conclusions with regards to the stability?
Can you assume it's stable because of the negative 5t? It's exponentially.
Yes, exactly. That's very good. So if you look at this negative 5t, what does this negative 5t correspond to? In the context of pole and 0, what is this negative 5?
The 0. The 0. Yeah, the polar transverses.
It goes to infinity,
Polar
right?
transverses.
No, what is this negative 5 in the context of pole and 0?
That's the pole.
That's the pole. Okay. So what you have to understand is, as long as the pole is negative, you understand? The system is stable. Does that make sense? So this corresponds to negative 5. You see that? And that means that, why is that stable? Because as this t goes to infinity, what does t going to infinity mean? It just means after infinite time. Okay? As t goes to infinity, what do you want the system to be? System response to be bounded. You understand? What happens if this is positive? As t goes to infinity, what happens?
The system gets more and more unstable.
Hmm?
The system gets more and more
Yes, so if you look at this, negative t, okay, your response is going to look like something like this, right? If this is positive, it's going to look like you see that? It's going to, the response is going to be out of your control. It's going to become infinite. So this, a negative pole means system is stable. Okay? Now this means it's a negative. Everybody understands that, right? Because S is equal to, how do you find the roots? How do you find the roots of any polynomial?
S equals to 0.
Huh?
S will equal 0 to S equal to
Right, so you essentially what you do is, if you want to find the roots of this denominator, again, roots of, you have to equate that to 0. Okay? This implies either S is equal to 0 or S plus 5 is equal to 0. Which this implies S is equal to minus 5. Okay? So do you understand time response and the role of poles and zeros? Got it? Okay. I'm going to say this is a first order system. Okay. Now tell me, what do you understand by first order system?
the highest degree.
The highest degree of the differential equation representing the system is 1. Got it? Now here, if you convert this to differential equation, what are you going to get?
Yes.
This is the solution to the differential equation. Okay? This is not the differential equation itself. You don't see dot, right? So this, if you convert this to differential equation, you're going to get C double dot of t plus phi, sorry, C dot of t plus phi C of t equal to
S, I mean C dot S.
R dot of t plus 2 R of t. Does that make sense? You just did this. I just multiplied this by this by this, and took the inverse of Laplace transform. Okay. Typically, you have to look at.
Why did you do that?
What do you mean by did it?
I'm saying, why did you do
I'm showing you the order of the system. So here, I just took the inverse Laplace of this. Okay, this is expressed. So here it is expressed as a transfer function. You can also express it as a differential equation, right? So if you write the differential equation, this is the differential equation. Okay, you have to look at what is your solution giving you. When you're looking at the solution, right? The solution is giving you what? This is the solution of the differential equation. You agree? What is the solution giving you? If you look at this, the solution is an expression for response or the output as a function of time. Okay. So if you look at what is the order of this response, the differential equation. This is a differential equation. First degree differential equation is C of t. Does that make sense? It's a first degree. It's the first degree of differential equation in R of t as well. Okay. But here we have to look at C of t. So where does the C of t correspond to? In this. here, look at the order of this differential equation. Okay. So I'll write it again. So this is the same. This can be written as C or D C of t over dt plus 5 C of t is equal to d over dt of r of t plus 2r of t. So these two are the same. Everybody gets that? Right? These two are also the same. Correct? What is the order of this differential equation? First order differential equation, right? It's a first order. Can you say it's a first order differential equation in C of t? Because you're taking the derivative of C of t. Right?
Yeah.
It's a first order differential equation in C of t. It's also a first order differential equation in R of t. Right? But if you look at the solution, so what do we do with this R of t? If you look at the solution, this is what response? The natural response. This is the forced response. This is because of the input, right? So you get that this is because of the input. So if you look at what is this differential equation, what does this correspond to? Does this correspond to numerator or denominator here? With regards to the transfer function. This part, the left hand side, the denominator. Okay, this corresponds to the numerator of the transfer. Huh? Numerator corresponds to the input. Okay. So if you look at this corresponds to the denominator. Now, can you figure out the similarities between the order of the denominator and order of this? What is the order of this? 1. It's a first order polynomial, right? This is the first order differential equation. So if you look at these two, you can look at just this and say that the order of this system is, look at the new denominator and say the order of the denominator of the transfer function is the order of the system. Does that make sense? So if this was so if I write, now tell me what is the order of this system, okay? What is the order of this system? Second order system. So you have to look at the order of the polynomial of the denominator to figure out the order of that system. You understand? You can look at this or you can look at the differential equation. What would the differential equation look like here? It would look like C double dot plus 4C dot of t plus 5C of t equal to R dot of t plus 2R of t. You got it? If you just cross multiply, this is what you are going to get. So you can compare the left hand side to the denominator and say this is a second order system. Okay? So when we are looking at response, So you see if this makes sense. If I have this, let's look at first order systems. Let's focus on first order systems. So this is T, alright? And this is, what would this be? C of T. So this is the step response of a first order system. Okay? How do I figure out the step response of this first order system? How do I plot it? If you were to plot it by hand, how would you go about plotting it? Anybody?
The solution or the differential equation.
How do you plot it? How do you go about plotting it?
I would start at A, and then I know what the exponentially decrease by.
Can you correspond? Can you see this here?
Okay. Yeah.
Hmm?
Yeah, you want to visualize.
Alright. When it's 0, it's going to be A plus B.
Hmm?
When T is 0.
Yes, exactly. So what you're going to do is, if you want to plot, understand what you need to plot.
Intercepts.
Hmm?
Zeros. Intercepts and zeros.
You need points, right? Do you need a table?
So,
If you want to plot something, what is the basic thing you need?
what's
You need points, or you need to construct a table of points, right? And an equation that is based on an equation. Now this is that equation. So what are the two things? You need at least 2 columns to plot something. Do you agree? Can you just plot one?
Oh,
It doesn't make sense, right? So here, what are those 2 columns?
You put it down.
independent features? Oh, CT.
You can see this. Now, see, here is my suggestion to you guys, okay? Listen carefully, guys. When you answer my question, when you try to answer my question, think about it. Look on the board. Don't guess. Okay? Do you see, that's the reason I'm saying, do you see this?
No.
C of T.
Yes.
T.
Yes.
So you input T, right? You get C of T. What do? You do T and C of T. How do you vary time?
Setting.
How do you input variables for time?
Chronological order.
Seconds? 0 second, 1 second, 2 second, 3 second. Can you do that?
Yes.
Yes.
So you can just, do you need a certain table or you can put it by yourself?
The T you do by yourself.
Huh?
The T you do by yourself.
Yeah, but you have to just calculate this, right? If this is 0, what are you going to get here? Hmm?
A.
Calculate and tell me. Huh?
You do.
You do get A? You sure?
Oh no.
E to the 0.
That's 1.
E to the 0 is
A
0.
plus B.
A plus B. You have to calculate, guys. You cannot guess. E to the power of 0 is what?
1.
1. So it is A plus B. You get it? So 1 is what?
E to the
A plus b
E to the negative
e to the negative 5. You see that? It will be 2 will be a plus b e to the power of negative 10. You see, this a and b are finite values. If I calculate these, I'm going to get that. You understand? These are finite values, right? So this will be some value. But you see how I'm getting these values? And then finally, where does this go to? Infinity. At infinity, what are you going to get?
It's gonna be close to zero, so it's gonna be eight.
Calculate and tell me what is that?
Zero, eight.
It will be a. Okay. All right. Now, if you look at is this increasing or decreasing the response? Think about it again. It's decreasing, right? So this is the largest value, and this is the this is the highest value. Okay. So if you look at this, all right. The response is going to look like now I'll tell you what is this is the let's look at this as so here this will be two over 5 divided by x plus 3 over 5 divided by into e to the power. Okay. So if I just calculate this, this will be 1, and this will be
What did you get 205 and 305?
where did I get this?
That's
How did I
the
get this?
value for A and B.
Huh?
Value for A.
It's value for A and B. It's just partial fraction expansion. Okay.
But he's saying.
So the response, I'm going to just talk about the response in this fashion. This is your C of t. Now, does this look right? Hmm? Does it look right? It should come. Hmm?
You gotta compare what
It's not, it's supposed to be a negative, right?
If you said it was positive,
So tell me what happens to the natural response?
It should be negative,
Hmm?
right? Or it should be a stable negative. Is that right? With the non-records?
it's gotta be the other way.
Decrease.
How's the story?
yeah, it's probably a 2-5. So why would that?
It starts with what?
How many goes down?
What is the natural response going to look like?
1.
So the natural response is going to look like, what is the highest value of the natural response? Which is the natural response? This part, right? So this is the forced response. Sorry, this is the natural response.
Yeah.
This is the forced response. You see that? What's going to happen to this?
Oh, no, but it's zero.
So if you look at the maximum value for this is,
The maximum is 5, the minimum is
maximum is 3 over 5, right? So if this is 3 over 5, this is the natural response.
oh, yeah, without the force.
Huh?
Without the force.
Right. And if this is 2 over 5, what is the forced response going to look like? It's just going to look like this.
Yeah.
It's a constant value, right? If you add these, will this look like this?
Nah,
Does it look like this?
nah.
So, C, that C of T, it has 2 lines on the graph all the time.
Yeah, these 2 lines. These are the 2 lines. This one and this one. All right, so let's look at this from a general point of view. All right, I agree. I won't give you this. So this is your. What is this line again?
That's your
The three.
natural response.
Natural or free response. Okay. And this will be forced response. So in time, or ultimately, what is going to take over? The forced response. The natural response will just decay. Okay. An example is, so this is the simplest example I can give you. If you're operating a fan, okay, you understand a little bit of electricity?
Sure.
You understand a little bit of electricity? Right? If you're operating a fan, when you switch on, is the voltage and current constant?
No.
No. At first.
Hmm?
At first,
Is it going to change?
Actually, if it's plugged into a wall, probably not. It might go like that.
It's not going to change at all. Okay. If you plug whatever is in this thing, when you plug it, it's going to be the current. The voltage source is anyways constant. Okay. The current is what is the current is equal to what? If the voltage source is constant,
This the
what is
variable,
current a function of?
The variable or time.
Current is not a function of. If voltage
not-
source is constant, what is current a function of? This is a very basic Yeah. resistance.
Yeah.
Right? Is the resistance of the fan going to change over time?
No.
It's constant, right?
Unless it heats up, right?
Huh?
Unless it heats up, right?
Unless it heats up, yes.
So, fan.
Fan, yeah. So the resistance of the fan does not change. You agree? Over time. So if you apply a certain voltage, it's going to draw a certain current. What's the natural response of the fan when you initially apply the voltage? What was the natural response of the fan?
To resist.
What is the natural state of the fan?
No current.
State.
State.
Off, it is not rotating. Okay. Understand Newton's first law. What is Newton's first law?
Object at rest, stay at rest until outside of the force.
Object in rest or in a state of motion will stay in that state unless acted upon by an external force. Okay. So if an object, if the fan is at rest, it will stay at rest. That is the state. What is the current used to then? What is current then?
Current is the flow of electricity.
In the context of Newton's first law, it's a force. It's an external force which will get you into motion, right? Once it gets into motion, what is the state? To stay in that motion, right? So what is the current used for then?
The force is created.
Huh?
Am I saying this?
What is the current used if this once the fan starts spinning,
To keep the fan at constant, to keep motion.
it will stay in motion according to Newton's law.
Today,
According to Newton's law, if it gets in motion, it will get in motion.
To keep the force response.
What is the current used for?
just create a response.
If an object in motion is going to stay in motion, why do you need the current?
Because it has to
Current
pass
Huh?
the resisting forces.
Resisting force. The only reason you want to use current at that point is overcome the resisting force. You understand? So that is that component. That force response is that component which will be used to overcome resisting force. Even your vehicle. What are you doing now? You're doing this all the time. You cannot work something else. It's, this is not acceptable.
Taking notes though. Doing this well.
You cannot do that.
Well past my point.
So think about this. When your vehicle gets in motion, is it using more gas or less gas?
Yes.
It's actually using more gas.
On set, when the vehicle is in
When it
motion,
gets in the
When it starts getting in motion, you're actually
it's using more gas when it's accelerating. That's what you're asking.
when it gets in motion, right? It's actually using more gas.
Because it has to continue to fight.
Yeah, it has to continue to fight resistance. When it gets in motion, what is the gas used for?
To push it.
My air conditioner.
What is the gas used for?
It's used to overcome the outside forces of the road. It's keeping
Road friction.
keeping it moving from fighting.
You understand? The gas is largely used for overcoming the road friction. The gas is not used to propel the vehicle itself. Okay, it is used to overcome the, because what does Newton's first law say? A vehicle in motion or something in motion will stay in motion. You understand?
Yeah.
That is what, and that is where orbits are perfect example of. If you put something in orbit, do you need any force to keep it going? So what is, it's obeying Newton's first law. Right? It will keep on. When will it stop? If you apply force, right? You get it? So your force response and this thing, if you look at, so let's finish with this. So now look at this. This is a generic first order system. A over S plus A, okay? And this is R of S, and this is C of S. What are the poles of the system? Jessica, what are the poles of the system?
The pole of the system would be negative A.
Negative poles, okay? It's only one pole, right? How many poles does a first order system have?
One.
It has to have just one pole. Now, what does this look like? What is the step response of this system?
A divided by S plus C.
Yes, absolutely. So it's A divided by S into S plus A. Got it? What is the time response? Can I write this as 1 minus e to the power of minus 80?
Yeah.
Okay. If you just do the partial fraction expansion, this is what you're going to get. Okay? This is a time response. If I plot this, now tell me to plot how it will look. What do I plot again? Always T versus C of T. Okay. What is the initial value?
R plus E.
0. What is the final value?
1.
Yes, I need you to calculate. If you cannot calculate quickly, write it on a paper and calculate. What is the final value? 1. Okay. So the initial value is 1 and the final value, initial value is 0. So if I plot it, will it look like this? What is the initial value?
0.
Zero.
Why is it 0?
Because 1 minus
1 minus 1 is 0, right? This will be 0, this will be 1, 1 minus 1 is 0. When this is infinity, this will be 0. It will be 1. Okay? So it will almost go to, this is at value 1. Got it? Now think about what are the performance parameters when you're looking for the response. What are the performance parameters you're looking at? Think about your vehicle. What are you looking from your vehicle with regards to performance parameters in the context of response?
Can you repeat the question?
You're looking at, let's say, an aircraft, right? The aircraft is going to respond to, what is it going to respond to?
The control.
It's going to respond to thrust,
Control.
right? Thrust is the force, that is the input, right? What are the response parameters, performance parameters? you need certain performance, right? You're looking at performance when you apply that thrust. What are some of the performance parameters you look at?
Speed, climb rate.
Efficiency.
Right.
You're looking at something like how fast it's going to reach a certain
Mach.
speed for takeoff, right? If you want to plan your length of the runway, you need to know how, at a certain speed it's going to start climbing, right? Now you need to know how much time is it going to take to get to that certain speed, so that you can plan your distance. So you're looking at something called rise time, settling time. Have you heard about this?
I heard rotation. And then,
You did not do this in the stability and control? Rise time control, rise time, settling time? No? So here, it's fairly simple. Okay? So here, this is, can I write this as C f of t plus C n of t? Does that make sense?
What is that? And
What does it mean? Force and mass.
That's just another way of writing it, or?
Yeah, this is C of t, right? C of t is always force response plus natural response. This is the force component, this is the natural component. Now the time taken at t equal to 1 over a, what are you going to get? What is C of t? Anybody? 1 minus e to the power of minus 1, which is 1 over 1 minus 1 over e. This is 0.63. Does that make sense? Because what is the value of e?
2.7 something.
Yeah, something like that. Okay. So 1 over e is 0.33. And if you 0.37, you just take a negative, you're going to get that. So your C of t, here is your 0.63. Okay. And what is this? What is this value?
One over A.
1 over a. So you can divide this into 1 over a, 2 over a, b over a, and so on. Okay. Here a is called the time constant. Does this time constant tell you anything? Does that tell you anything?
time is constant.
It's one
You
value.
can't change time.
Time
Right.
changes, but
Like, time keeps going, it never stops. Right.
What does this signify
a specific point in time.
with regards to response?
Because you don't know what it is.
It's the pole, right?
It's the pole, but time constant is the time taken by the system to reach 63% of its final response. Does that make sense? Does that make sense? Yes?
So it's the time taken by.
What is the final response? Huh? 1. Right. What is 63% of the final response?
0.63.
0.63. How will you get that? When you substitute t equal to, this is that time, okay? It's actually 1 over 8. You understand? This is actual time period. So the time taken by the system to reach 63% of its final response.
So that's consistent, it's not gonna change from 63%.
Yes, so if you example, think about this. What is this time constant of? What is the time constant here?
It should be 63%, right?
What is the time constant here?
2. Yeah, then you have to extend up to her.
So compare the denominator, the roots of the denominator.
Oh, it'd be 3.
1 over 3.
Whatever.
Okay. So the time constant here is 1 over 3, which is equal to 0.33.
So now it's 33% of your final response.
This is what? What is the unit of this? Seconds. Okay. In what you want to say is in 0.33 seconds, right? C of t would be what?
1 over 8. 63%.
0.67 for unit 63%. Or this is 63%. Does that make sense?
So no matter what your time constant will say, like how long it's taking to get 60%.
Right. So if you look at, this is one example. Another example is, if you look at this, okay. What is the time constant here?
0.25 seconds.
0.25. So in 0.25 seconds, what is the system response? How much it is going to be? 63%. Okay. So which is faster? The second one. You get that? It's a parameter. It's a performance parameter. Like you want to know. Compare this to something like this. You have these values where you say from 0 to 60 in 5 seconds. This is comparable to that.
So the 63% in like 0.25 seconds.
Yeah. So you don't, 63% is like, it just relates to this. So this is, the first order system is always going to look like this. You see that? This pole will correspond to 63%, the time constant, the amount of time taken to reach 63% will be that. You get it? So your rise time, we'll discuss this next time. But understand this. You understanding this response, how it looks, and what this time constant is?
Yes.
If I ask you to calculate the time constant, if I give you a system, can you calculate the time constant?
Yes.
Okay. Now, tell me, what is if I define rise time as the time taken by the system to reach 63% of its final value. Okay. Rise time as the time taken by the system to reach 63% of its final value. What is it equal to? 1 over 8. Yeah, it's time. You get it? If I say the time taken by the system to reach 90% of its final response, you will just substitute C of t equal to 0.9 and figure out what that t is. Yes.
Is it helpful to make the midterm